To create a bandpass or band reject filter, we must introduce inductors into our filters, and so these are sometimes called RLC filters. And in using these, if we measure simply across the resistor, then what we will create is a band pass filter. And in the opposite situation, if we measure across the capacitor and the inductor, we will get a band reject filter. And again, all three of these components are going to play into the behavior of how our filter operates. And if we recall, our filter is largely described by how the transfer function works. And so, say for the sake of an example, if we were going to make a band pass filter, traditionally our filter would start very low and it would rise and then come back down to a level, and that these values right here would be indicating to us the corners of the particular band region in which this band pass filter operates. And then we will also have a center frequency or a resonant frequency that gives us the center of the band region. So with this drawing of the transfer function, we can highlight a couple important elements. One, again, is these corner frequencies that give us where the filter begins to operate. And our corner frequency is the same definition as before. It's either the half power point or where our magnitude of our transfer function is at 0.707%, or which is the same thing as divided by square root of 2. So this value for our corner frequencies is always going to be the same. This resonant frequency or center frequency is going to be the middle, generally, between these two cutoff frequencies. And so we can define a new quality called bandwidth that tells us the difference in terms of frequency between those two bands. And so the more narrow a band is, the more sort of discriminating a filter is going to be. It's going to only affect a smaller range of frequencies, versus a wider bandwidth is going to indicate that it'll affect a lot more frequencies. And related to this is going to be the concept of quality. And so a filter that has a more narrow bandwidth is going to have more quality to it. So let's take, for example, and say that this filter right here has a quality of 1. And we look at this bandwidth and it's a little bit too large, and so we narrow it. And so we can take our band here and let's say we narrow that bandwidth, and now it has a quality of 5. And again, we analyze our circuit and maybe we want even a tighter bandwidth, and so we end up with something like this, and that might have a quality of 10. And so the relationship between the quality of a filter has to do with the relationship between the center frequency of the filter and the bandwidth. The tighter the bandwidth, the higher the quality of the filter. And as we will see in a bit, this is related to us by the components in our circuit of the resonant frequency and our inductor value over our resistor value. Now, for any filter, whether it's a band pass or a band reject, that filter is going to have a center frequency or a resonant frequency where the band region is centered. And for an RLC filter, that center frequency can be expressed as 1 over the square root of L times C, where L and C are the capacitive and the inductive elements in our circuit. In addition to having a center frequency, we again have corner frequencies that dictate the width of our bandwidth and begin to tell us where our circuit begins to operate. And these values are functions of the entire circuit, and so the expression for the corner frequencies is a little bit longer, but it relates the resistance and the inductance along with other components in the circuit. So this is our entire expression for what the definition of the corner frequencies are. So the corner frequencies deal not only with the inductance and the resistance and the capacitance, that is a C there. But they involve all three factors of the circuit. Finally, we said that there was a third parameter, which is called the bandwidth, and we will just mark that as a B. And the bandwidth of our circuit is going to be the difference between our two corner frequencies, and that is always given to us as R over L. So one of the particular challenges we will have with second order filters is that if you change one of these particular parameters, it's going to affect all of the other parameters in the circuit. And so care needs to be taken that you select parameters that you can actually pick and build in the circuit, but also understand that if you change one parameter, it might affect other elements of the circuit. The selectivity of a circuit we discussed as this idea of quality and represented it as the ratio of the center frequency to the bandwidth. And as we plug in our other definitions here, we can find that our center frequency times our inductance over our resistance will also give us our quality. One final thing that's sort of missing in here is what is the relationship between sort of this center frequency and these corner frequencies. And an assumption we can make is that if our quality is good enough, meaning that our quality is sort of greater than a value of 10, we can assume that that center frequency is actually the halfway point between our center point and our corner frequencies. And so we can use that to say that if we have a filter of sufficient quality, then we will be able to dictate simply the bandwidth and the corner frequencies, the bandwidth and our center frequencies, and our corner frequencies will end up in the correct spot.